Okay, welcome back to another TCX1004 video, and let's pick up where we left off from the previous one where we talked about big O, and now we're going to combine that with induction. So in this video I'm going to show you something called the substitution method, right, which is kind of a cousin of the proof by induction method, but it's very streamlined and it's very simple, so it makes our lives a lot easier. The proofs look a lot leaner. Okay, so here's how it goes. Let's go back to looking at some Python code again. Let's say we want to compute the factorial, right? And if you don't remember, factorial is basically just 1 times 2 times 3 times 4 all the way until n, right? So here's a program that does it, but it does it recursively, right? So instead of writing a for loop, I've written it this way instead, where basically to compute the nth factorial, we will compute the n-1 factorial and multiply it by n. Okay, sometimes you will actually see programs that are written this way. Sometimes things can be written with a for loop. Sometimes things are more naturally written in recursion. So here's my simplest example of a program that is written in recursion. Okay, so why am I bringing this up? Well, because the question I'm going to ask is, what is the running time of this program? In particular, if you think about it, we might be given a recursive program at some point and we kind of need to analyze it, right? So how do we do this? Well, there's kind of two steps to this. The first step would usually be to find the recurrence that corresponds to this program, which is technically not under this module's like purview. So we won't really be doing that. But the second half, which is to bound the recurrence that we have, is very much our business, right? So in other words, what I'm saying is that let's just say I magically told you that this was the recurrence that corresponds to this program. And by the way, this is hopefully not too hard to see, right? So in case 1, when n is equals to 1, the amount of work we do here, I'm going to say is O1, right? And the case when n is greater than 1, well, then it's written as Tn-1 plus O1. What's the reason for this? Because, well, we're calling our program again, right? So to call our program again, the amount of work that we had to do to compute the n-1th case is written as Tn-1, right? And the amount of work we had to do at our current level was O1 because we had to multiply the value and return it, right? So that's kind of how it looks like to translate a program to a recurrence, right? But again, that's not really our concern. Our concern is more of how do I prove that this program, that this recurrence, let's say, Tn is On, right? And if we were to prove that Tn is On, what we would have effectively done is shown that the larger the value of n, right? Like if I doubled my value n, the running time of my program also doubles, right? So how do we prove this? We're going to use something called the substitution method. Okay, so let me show you how to do it. I'm going to show you an example of a proof first before we talk about the features of the proof. Here's the idea. We're going to need a constant factor because if you remember from big O, there's always a scaling factor involved, right? And typically it's very simple. Typically it's 1. It's not always 1, but typically it's 1, right? So let me set c equals to 1. That's our scaling factor. And we're going to assume that for all m less than n, right, Tm is less than or equals to c times m. Hopefully this is intuitive to you, right? The reason why this is true, I mean, this is, like what you would want to do in strong induction. We're basically just doing a very streamlined version of this argument here. Okay, so now we've assumed it for all values less than n. We need to prove it for n, right? So let's take Tn, and typically we need to expand the definition of Tn, which happens to be n-1 plus 1. Okay, this is by definition of Tn. Well, then we know that by our assumption, right, we could have replaced Tn-1 with just n-1, right? This is because we assumed that for all m less than n, n-1 happens to be less than m, so we can replace Tn here with n-1, and we had a plus 1 on the side. But if you realize those two things just cancel out, and this is less than or equals to c times n, right? So few features of the proof to note here. Even though the recurrence is written with O1, we're just going to replace that with 1. There is a reason why this works. It's a little bit complicated. Just take my word for it that we're simplifying things a little bit here. Okay, and the reason why, again, let me stress, the reason why we could sort of make this replacement with Tn-1 to n-1 is because we made this assumption that for all values less than n, it is true, right? And then finally, we want to conclude exactly what we want to state, which is that Tn is less than or equals to c times n, right? In other words, there is a scaling factor multiplied by n, Tn will be less than or equals to it. Okay, one other interesting thing you might have noticed, now there is no need to show a base case in the substitution method. right? This is why this is our favorite method for bounding recurrences, because it's very streamlined, it's very simple, it's very straightforward, right? Okay, so let me go through a negative example before I show you two more examples, right? Two positive examples. So let's say, for example, that we have this other recurrence, Tn. It happens to recur on two things. One is n over 2 floor and one is n over 2 ceiling, right? And then we add 1 to it and continue. Okay, so and let's say there's a basis of n equals to 1, and we want to show that Tn is less than is in O of n. Okay, so again, if you remember what we did in the previous one, maybe we can do something like set Cn to C to be 1, and then we make our assumption here. Again, we want to show it's in O of n, so we're going to assume that Tm is in less than or equals to C times m, right? And then again, we just unpack our definition, right? So Tn here is equals to, by definition, Tn over 2 plus Tn over 2 plus 1. Okay, well, by our assumption, then we can replace these two lines, these two recursive calls with just the values themselves, because that's what our assumption says we can do, right? And also carry over the plus 1. Okay, well then after that, in that case, what we can do is just replace the two terms. If you sum it up, it's just n plus 1, right? The problem now is that we did not match our original assumption, right? Because our assumption was to prove that it was less than n, less than m. So we have to match the assumption by proving it's less than n, right? But instead we prove that it is less than or equals to n plus 1, which is basically not fulfilling our end of the deal. Okay, so to fix this, here's the way to do it. We know the term that we have to compensate for. We're just going to subtract away from it in our assumption. Okay, so to do that, what would happen is that the proof changes a little bit. So the second line now, there's a -1 and a -1. And if you realize, this cancels out and it becomes a -1. And now we get n minus 1, right? Which actually matches our assumption this time around, which is great. This is exactly what we want to see. Okay, so now that we've mentioned that at the very least, let's go through two more examples, right? So this time around, let's say I have this recurrence where we make two recursive calls to n over 4 and we add 5 to it. Okay, so again, I'm going to basically write this down with C as a multiplier of 1, and I'm going to assume that Tm is less than or equals to C times square root of m minus 5, right? So let's see how this works. So Tn by definition is 2Tn over 4 plus 5, right? And then if I were to replace the Tn term with our assumption, our assumed value, right? So it's just going to be 2 times square root of n over 4 minus 10 because there's 2 times minus 5, right? Plus 5. So we can resolve the term on the right. So minus 10 plus 5 becomes minus 5. And I'm going to remove the floor on the fraction, so it becomes n over 4. And basically this is just square root of n minus 5. So we've basically, again, met our assumption, right? So hopefully you see how quick and easy it is to use the substitution method. It's after this we can conclude that t is in square root of n. Okay, so let's do one more example. This time around, I'm going to show you Tn being 2 times Tn over 2 plus 2n log n. And this time around, we want to show that this is in n log squared n. Okay, so how do we do this? This time around, I'm going to use the multiplier. So I'm going to set the multiplier to be 2. Okay, and I'm going to assume that for all m less than n, it holds that Tm is less than or equals to C times m log squared m. Okay, so how does this work? Well, Tn, again, by definition, is 2Tn over 2 plus n log n. Right, and then that's by definition. Again, replace it with our assumption. Our assumption here was that we can replace this by n over 2 times 2. That 2 here is the multiplier, that's the C, times log squared n over 2, right? Well, then I'm just going to rewrite this. So I know that if we divide by 2, right, that's just minus 1, and it's the whole thing squared, right? So in the middle, I'm just replacing this with log n minus 1, the whole thing squared. And then basically, since we're just squaring this portion, we can write this as log squared n minus 2 log n plus 1. Okay, so let me resolve the terms on the outside as well. So 2 times n over 2 times 2 is basically just 2n. Okay, then I'm going to distribute the terms. So 2n distributed across the entire parenthesized portion just gives me 2n times log squared n minus 4n log n plus 2n. Okay, so let's look at the last part here, this last three terms. Well, 4 n log n plus 2n plus 2n log n is actually negative, right? For large enough values of n, this is negative. And if it is negative, then removing these four terms together only gives me an upper bound, right? Because I'm removing a negative term. Okay, so this gives me that Tn is less than or equals to n log squared n, which again is what we assumed, for all n less than n, we're just holding our end of the deal, right? So we've basically proven that Tn is in O of n log squared n. Okay, so this again was the substitution method. In conclusion, it's a quick and dirty way to prove recurrences are in big O of certain types of sets of functions, right? And if you ever have to prove a recurrence is in big O of something, this would be the way to do it. Hopefully you realize and notice how quick it is. Okay, so moving on, we're going to go on to the next video where we're going to use induction again, but not to analyze the runtime of programs, but instead to prove the correctness of programs instead. See you in the next video.